Welcome to Pomodoro Joe for Friday, June 16th, 2023. Today we're doing LeetCode problem 1569, number of ways to reorder array to get same BST. This is a hard problem. Given an array nums that represents a permutation of integers from 1 to n, we're going to construct a binary search tree, BST, by inserting the elements of nums in order into an initially empty BST. Find the number of different ways to reorder nums so that the constructed BST is identical to that formed by the original array nums. For example, given nums 2, 1, 3, we have 2 as the root, 1 as the left child, and 3 as the right child. The array 2, 3, 1 also yields the same BST, but 3, 2, 1 yields a different BST. Okay, so that's interesting. So this first one is going to be the root, because that's the first one we put in the tree. Then we can put either child in the tree next. We can do 1 first, or we can do 3 first. All right. But this 3, 2, 1, 3 will be the root, 2 will be the right, and 2 and 1 will both be in the left. Okay, so this is a different BST. Return the number of ways to reorder nums such that the BST formed is identical to the original BST formed by nums. Since the answer may be very large, return it modulo 10 to the 9th plus 7. All right, and then we have some examples here. So we have 2, 1, and 3. So we have to put 2 in as the root first. Then we can put 1 or 3. Doesn't really matter which one goes first. So we have 2 options. We put 1 or we put 3. And the output is going to be 1 because there is only one additional option. There are 2 total permutations, but only one additional permutation from that original array. All right, then we come down here. We have 3, 1, 2, 4, 5. So 3 has to be the root, so 3 will always be first, and that looks like we got that. Then we can either choose to put 1 in, or we can choose to put 4 in. If we choose to put 1 in, then we can either put 2 or 4 next. So we should have a 3, 1, 4 and a 3, 1, 2 as options. So 3, 1, 2, yep, 3, 1, 4. So if we do 3, 1, 2, then we have to do 3, 4, 5 after that. So 3, 1, 2, yep, 4, 5. We have 3, 1, 4. We can either do 2 or we can do 5. So we can do 3, 1, 4, 2, 5, or we can do 3, 1, 4, 5, 2. 3, 1, 4, 2, 5, 3, 1, 4, 5, 2, yep. And then alternately, we can do 3, 4, and then 1, 2, or we can do 3, 4, 5, 1, 2. 3, 4, 1, 2, 5, 3, 4, 5, 1, 2. All right. All right, so I don't have a lot of time today, so I'm going to go through this super quickly. Then I will come back. Hopefully, if I have time, I will come back and do some more explanation about how we do this one, because this is definitely a tricky problem. All right, so we will start by putting our result, and we will have 0 as our initial result. Now at the end, we will return our result modulo 10 to the 9th plus 7. So let's do that here. All right, now for this one, I want a recursive solution. So if we find all the permutations of our left branch and our right branch, then we can use those to find the permutations of our current tree. So we'll have some, let's see, num ways recurse. And this will take our current tree. All right, now we have our base case. Now, if we only have 1 or 2 nodes in our tree, there's really only one option. So we have to put the root, or we can put the root and then the left or the right if we only have 2 nodes. If we have 3 or more nodes, then we have more options. All right, so we'll start with that. If our length of tree is less than 3, then we return 1. There's only one option. Now, if we have more than 3 nodes, this is where it gets extra complicated. But essentially, let's see, we'll take our root. Our root will be nums at this tree. Do I want to say nums at tree? No, I want to say tree at index 0. So the root of this tree will be this tree's index 0. Now we have to put that one first. There's no other option. Then we have our left branch and our right branch. So let's do a left tree. And what's in our left tree? Well, that's going to be all of the numbers that are less than this root. So all the numbers left in this current tree that are less than this root. So this will be n for n in tree if the n is less than this root. And for the right tree, kind of the same thing, but only for values greater than our root. So the right tree, let's see, n for n in tree if n is greater than root. So now we've broken out our left tree and our right tree. Next, we need to actually find combinations of these values. Now, this is where I'm not going to have time to explain it right now, so I will just do the combinations as an n choose k type problem. So our n, well, how many numbers do we have left in our tree? Well, we have to choose our root. Every time the root has to take that first spot. So we only have our tree, the length of our tree minus 1 spaces left. So we have the length of tree minus 1 n, that's how many spaces we have. And then how many combinations can we choose within this space? Well, this is also where it gets complicated. We either choose our left tree or our right tree. We need to keep our left tree ordering the same or our right tree ordering the same. So if we choose our left tree, then we can basically spread out all the different elements of our right tree in between our left tree elements. So we have essentially right tree elements in which to play around with. So that's how many k we have. So we'll say it's the length of the right tree. Okay, so at this point, we're taking our left tree, we're spreading it out among the remaining elements. And so our remaining elements, let's see, we will have to return, well, we'll have the left, oh, let's see, we didn't do our options yet. So we need to get our options for the left tree. All right, so how many different combinations are in the left tree? Well, this is our recursive call. So num ways recurse, and we're going to pass in the left tree. And then we have right options. So how many different combinations are in our right tree? Well, that's the number of ways to do the right tree. Okay. Now we get to our return value. So at this point, we can return the number of ways to do the left tree, the left options, times the number of ways we could do the right tree. But then we need to find these different combinations of permutations within the left or the right. Now, since we are doing, whoops, I missed my parentheses here. Since we're doing the right tree here, then these are going to these will be the permutations of, I guess we've already broken this out into k and n, so it doesn't really matter if it's left or right. So we just use the combinations. Now I'm cheating a little bit because I don't have time. I'm going to use the combinations for, this is the Python combinations. It's in the math library. If you don't have access to a combination type library like this, you can do your own factorials to figure out combinations. But for now, I just don't have time. So I'm going to use the combinations. And again, we already chose our n and k. We already broke our n and k. So we just have n choose k. All right. So these are our different options. And out here, I guess I'm missing my recursive, my initial call. So the initial call, our result will equal our num ways recurse, and we'll pass in our initial tree. So that's just nums. All right, I'm just gonna copy and paste this to make sure I don't have typos. All right. Okay, so I think this should do it. We're going to basically grab our root. It's going to be the first thing in our list. We don't have a choice there. Then we'll grab all the different ways we can create the left tree and all the different ways we can create the right tree. So first we have to grab the elements that create the left tree. So that's every element in the tree that's less than our root. And for the right tree, it's every element in our tree that's greater than our root, because this is a binary search tree. Next, we will actually create or grab our options. Let's see, I did this in the wrong order. It doesn't really matter, but next we'll grab all the different ways we can do the left tree, or the permutations for the left tree, and that's going to be the recursive call on the left tree, and then the permutations on the right tree. And then this is where we do this sort of pickup slack where we can spread our left tree elements out in between all of our right tree elements. And for that, we actually have how many elements are left in our tree. That's our total number of spaces in our array. Then we choose either the left or the right tree. It doesn't really matter. And we'll spread out the elements of the other tree among these remaining elements. So anyway, again, I don't have a lot of time. I'll come back and try to explain this later. Let's see if this works. I have a runtime error, length of tree -1. Oh, that's because I need to do length of tree -1. All right, let's do that. And we fail. Okay, what am I missing? So I go through the length of the tree, -1. The length of the right tree, all right. I have my left options, I have my right options. Okay. Oh, because I need to remove, so this is going to find all the different combinations, but of course, one of the combinations is the original input, so we need to remove one from our final output. All right, that was a silly mistake. Okay, let's submit that and see if we pass. And we pass, and we do pretty amazing actually. We beat 97% for runtime and 61% for memory. That is crazy good. Just to show you really quick, it doesn't really matter if you choose left tree or right tree here. We can swap this out. We can say this is the left tree. As long as you are consistent between your recursive calls, it doesn't really matter. Let's just make sure that still works. Yeah, that still works, and we can submit this and see if we still pass. It might not get the same percentage. Yeah, it's a little bit less. We get a 95% for runtime, 51% for memory. Yeah, so it's about the same. Anyway, that is it for me. I am totally out of time. I gotta go. I will try to make a video later to explain this because this is definitely a confusing one. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.